Good evening, everyone. I am extremely happy to be part of this webinar presentation to the EEE and ECE students of KITCBE. So this presentation is on success to gate through control systems. So in this connection, I would like to thank Dean Center for Industry Institute Interaction, KITCBE, Dr. Mahalakshmi, for inviting me as a resource person and presenting the same before the EEE and ECE students of KITCBE. I am also grateful to the management, principal and faculty members of KITCBE for this opportunity. Let me move on to the presentation straight away. Before going to the gate control systems, let me quickly review or recall what has happened in the past gate examination, that is gate 2020. If you look into the various disciplines, electronics and communication engineering, electrical engineering, chemical engineering, instrumentation engineering, the qualifying marks out of 100 for general category, 28.8 in the case of ECE, for EEE 33.4, chemical 35.7, instrumentation 34.6. So I am sure the students of EEE and ECE will be eager to definitely surpass this score. And if you look into the question paper pattern, so we know very well that we have 1 mark question as well as 2 mark questions, and we have multiple choice questions as well as numerical answer type questions. For multiple choice questions, there will be negative marking, 1/3 mark for 1 mark multiple choice questions, 2/3 negative mark for 2 mark multiple choice questions. However, no negative marks are allotted for numerically answered type questions, whether it belongs to 1 mark or 2 marks. And you can see in the general aptitude, there are 5 questions with 1 mark and 5 questions with 2 marks, that is totally 10 marks. So one can get 15% through general aptitude. So general aptitude means some general science, English. So very general, which we can easily score. And if you look into the engineering mathematics, it is again carrying 15 marks, 5 marks in the 1 mark and 10 marks in the 2 marks, like GA. So totally 15 plus 15, 30% contributed by general aptitude and engineering mathematics. The core discipline questions, they carry 70 marks out of 45 questions, 21 mark questions, 25 2 mark questions. And I can definitely guarantee that 15% can be scored in this core discipline only with control systems. So if you are strong in control systems, I am very sure you can score 15 marks quite easily. This I have found out when I have thoroughly gone through all the previous 5-year question papers pertaining to electronics communication, electrical, chemical, instrumentation. So in all these branches, they ask 15% of the questions from control systems. So let me move on to the solution to control systems. Just for the illustration purpose, I have taken some 15 to 20 questions. So based on the time, I will try to cover as much as possible. And if you have doubts, you can ask me at the end. Even you can ask me through the email ID or the WhatsApp number that I have given at the end. So the objectives of my presentation is to understand the tricks of qualifying gate and exploit the scoring opportunities for entering public sector units, and especially to enter into higher level institutions also for higher level learning, to analyze the style of preparation for learning any course, to score as much as possible in control system. This is what I have already mentioned. First question, it is actually taken from GATE 2020 Electrical Engineering, question number 10. So a linear time invariant system whose input and output are related by a differential equation. So it's a second order differential equation. D square I by dt square plus 4 dy by dt equal to 6r. So it is a second order differential equation. Poles of the system are. So four options are given. Poles means what? Poles means nothing but denominator roots, roots of the denominator of the transfer function. Therefore, we have to first of all take the Laplace transformation with zero initial conditions. I hope you have studied in control systems how to find the transfer function. So take the Laplace transformation with zero initial conditions. So d square I by dt square means it will be s square y of s. 4y of t will become 4y of s. 6r of t would become 6r of s. Therefore, y of s by r of s, the transfer function is 6 by s square plus 4. So 6 by s square plus 4 means s square plus 4 is the denominator polynomial. So roots of the denominator polynomial, if you find out s square is minus 4, s is equal to plus or minus 2j. So plus 2j minus 2j, they are the poles. See how easily you can score with just one or two steps. Only thing is you should know that this is so much easy, that's all. So if you definitely feel that this is how you can solve this, I am sure you can solve all the problems in control system which I am going to explain. Second problem, it is taken from GATE 2019 Electronics Engineering. The block diagram of a system is illustrated in the figure shown, where x of s is the input and y of s is the output. The transfer function h of s is equal to y of s by x of s is what? So they have given x of s, y of s and the block diagram. What is the transfer function they are asking? That means this is the problem on block diagram reduction or signal flow graph, that's all. Of course, this can be solved using block diagram also, but for the sake of simplicity, I have solved using signal flow graph, because you might have studied in control systems that solving the block diagram problem using signal flow graph is very, very easy. So here, how to choose the nodes you should understand. So x of s is the input node, y of s is the output node. Okay. Then here you have a summing point where this signal is added, signal from this summing point is added, and signal from the output is added. Therefore, you should have node here. Yeah, you should have a node here. You can see signal from the input. Of course, I will tell how this is done and how this is done. So for the time being, you can easily understand that there are three input signals, right? Then output of this summing point should be fed to another summing point through two different gains with s and 1 by s. Yeah, it is fed to another node. Summing point means node with gain s and here with gain 1 by s. Same thing I have reproduced, right? So this output only should be fed here. Yeah, this output is only fed here. Then output of this you should multiply with a branch 1 by s. Multiply with a branch 1 by s. Yeah, that is the output. That output is also fed to this summing point. Yeah, we know that output node is a node with only incoming signals, but here you have incoming as well as outgoing. So the definition of output node is not satisfied. Therefore, a branch with unity gain is taken and is called y dash of s. If you want, you can take, or even you can do straight away. Right. Once you draw the signal flow graph, the next procedure is to find out the forward paths and loops and apply Mason's gain formula. So what are the forward paths? Path from input to the output. So you have one path here to here, here to here, here to here, here. So 1 into s into 1 by s into 1. So P1 is 1. So first forward path. Next P2. So you can go like this, like this, like this, and like this. So 1 by s, 1 by s. So 1. So if you multiply all that, 1 by s square. Right. How to find out delta 1 and delta 2? What is delta 1? Delta 1 is delta of that part of signal flow graph in which first forward path is removed. What is the first forward path? This is the first forward path. For that only we have found out P1. if you remove the first forward path from the signal flow graph, all the nodes will be removed. Therefore, nothing will be left out. If nothing is left out means delta formula is 1 minus sum of individual loop gains plus sum of gain products of two non-touching loops, etc. So that second term, third terms will be 0. Therefore, 1 minus 0 is 1. Similarly, P2, if you remove the second forward path, that is this path gain, if you remove this path, then all the nodes will be removed. Therefore, delta T is also 1. Now we will see how to find out the loops. So how to find out the loops? Loop is a path which originates and terminates at the same node. So first we have taken P11 equal to minus S. So how we got that minus S, we will see. See, from here to here, here to here, that's also, this is a path. This is a path. So P11 is minus S. Then from this to this, this to this. So minus 1 by S, that is another path. Then this to this, this to this, this to this. So S into 1 by S into minus 1. So 1 into minus 1 is minus 1. Next forward, the next loop is 1 by S, 1 by S, minus 1. So minus 1 by S square. So I think I have traced all the possible loops. Right. Next we have to see the non-touching loops. Fortunately, all the loops are formed with this node. This node is common to all the loops. Two loops are said to be non-touching if and only if they do not share any common node. But there is a common node, therefore no non-touching loops. Therefore, we can straight away write the expression for the transfer function. What is the transfer function expression? Sigma pk delta k divided by 1 minus delta. What is pk delta k? So there are two forward paths. Therefore, p1 delta 1 plus p2 delta 2. So p1 delta 1 plus p2 delta 2. That's all, divided by 1 minus sum of all individual loop gains. Just now we have seen all the loops. So 1 minus p11 plus p12 plus p13 plus p14. So all these are substituted, and here we have taken the LCM, and if you take LCM and simplify, you get S square plus 1 by S cube plus 2S square plus S plus 1. So this fits into option B. So option B is correct. See how easily it is solvable. Only thing is, we should know that this method we have to apply for this particular question. That's all. If we get that strategy correctly, I don't think you will find it difficult to solve any problem in gate control systems. So let me move on to the next problem. So here the signal flow graph is straight away given. Gate 2017 electrical engineering set 1 question number 32. So there are two inputs U1 and U2. The transfer function y of s by U1 of s is asked. So there are two inputs and one output. The question is y by U1 of s. So whenever we want to find out output due to two inputs, we know very well that transfer function concept is applicable only to linear time invariant systems. And for linear systems, when we find out the output due to one input, other input can be taken as 0. That's all. Therefore, you take this as 0. Therefore, 0 into minus 1. Therefore, you need not consider this branch at all because 0 into minus 1. So this you can forget. So we want to find out y of s by u1 of s only. Therefore, this only we have to see. So this problem becomes a simple problem. So what is the first forward path? From here to here, here to here, here to here, here to here. So 1 by L, 1 by S, K1, 1 by J, 1 by S. So if you multiply all K1 in the denominator, K1 in the numerator. So denominator L, S, J, S. So JL square, that's all. There is only one forward path because you cannot go like this. Similarly, you cannot go like this because your direction and the branch direction, signal direction, they are different. So there is only one forward path. If you remove the only one forward path, what will be delta 1? 1 like previous problem. That's all. Next, loops. So what are the loops? So simple loop is this. So 1 by L into 1 by S into minus R. Yeah, minus R by SL. What is the other loop? This to this, 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 this to this. Am I right? Yeah. Yeah. So you just multiply the gains of all the branches involved in the loop. That's all. So 1 by L into 1 by S into K1 into 1 by J into 1 by S into minus K2 if you do minus K1 K2 by JL square. That's all. So in the both the loops, while forming both the loops, this node and this node, they are common. Therefore, no non-touching loops. Therefore, we have to write the transfer function in the same way like previous problem. So here, in the previous problem, P1 delta 1 plus P2 delta 2. Here it is only P1 delta 1. In the previous problem, 1 minus P11 plus P12, P13, P14. Here there are only two loops. So 1 minus P11 plus P12. Simply substitute here, take LCM, simplify, that's all. So if you simplify, you get this expression. Which of the four options fits into this expression, we have to see. Fortunately, option A fits into this. Option A is correct. See how simple the problem is. So let us move to the next problem. The relationship between the force and the displacement of a spring with the mass, viscous damping and spring constant is given. So this is a very famous equation. F of t is md square x by dt square plus d dx by dt or b dx by dt plus kx, where x of s and f of s are the Laplace transforms of x of t and f of t respectively, with m equal to 0.1, d equal to 2, k equal to 10 in appropriate units. The transfer function g of s equal to x of s by f of s is, four options are given. So first we have to take the Laplace transformation on both sides of the given differential equation. Because we are asked to find out the transfer function, that's all. So if we find out the transfer function, what will happen to md square x by dt square? S square mx of s. This is s dx of s. Kx of s equal to f of s. So what is x of s by f of s? Simply this. So substitute the values of, they said appropriate units, standard units. Substitute the value of m, d and k here. So that's also 1 by 0.1 s square. M is substituted, d is substituted from here. So 2, k is 10, so k is 10. That's all. So we have to fit into one of these expressions. Nowhere 0.1 is coming. So you can multiply both numerator and denominator by 10, or you can take 0.1 outside. Both is giving the same result. So 10 by s square plus 20s plus 100 if you multiply both numerator and denominator by 10. So this fits into which of the four options? This option. So option A is correct. See how simple it is. So that is why I said solving gate problems in control systems is very simple. If you understand this, I am sure you will score as much as possible in gate control systems. Full marks you can score. Next, GATE 2016 Electronics Engineering set 3 question number 20. For a unity feedback control system shown in figure, the open loop transfer function is given as. So they have given the open loop transfer function. Steady state error due to a unit step input they are asking. So h of s is 1. So we know steady state error for a step input. Steady state error for a step input, we know it is 1 by 1 plus kp. We have studied in error chapter in control systems. 1 by 1 plus kp. What is kp? Kp is nothing but position error constant. What is position error constant? Limiting value of g of s h of s as s tends to 0. That is limit s tends to 0, g of s h of s. H of s is 1, therefore g of s we have to simply substitute here. So kp is as s tends to 0, it is infinity, so it is 0. In fact, we don't have to even do like this. We can straight away write 0 because it is a type 1 system. Whenever you have only one pole at origin, see type 1 system subjected to a step input always tracks the input at 0 steady state error. This is the thing that you would have studied in control systems. So from that you can straight away write 0, no need to do even these two. Suppose you forgot that, then you could probably do this. See how simple it is. Next, the output response of a system is denoted as y of t and its Laplace transform is given by y of s equal to 10 divided by s into s square plus s plus 100 by 100 to 2. The steady state value of y of t is, so they have given four options. So here they have given one output in Laplace transformation. They are asking steady state value. Just because they have asked y of s, don't think that you have to take inverse Laplace transformation and find out y of t. You should see in which method, simple method, this problem can be solved. Always the strategy to score good marks is to choose the simplest method to solve the question. So here steady state value means immediately what you should get in your mind is, or what should strike your mind is, final value theorem. So if you know how to apply final value theorem, it's very easy. What is final value theorem? Limit t tends to infinity y of t equal to limit sn into 0 s into y of s. That means a time domain output is related to s domain output using final value theorem. So final value is substituted in time domain, initial value is substituted in s domain. That's all. Limit t tends to infinity, f of t is limit s into 0 s times f of s. You have studied in Laplace transformation, same thing. So y of s they have given, so that y of s we have to simply multiply by s. S cancels. As s tends to 0, 0 plus 0 plus 100 root 2, 10 by 100 root 2 is 1 by 10 root 2. So option E is correct. See how simple it is. So if you know how to use the final value theorem, this is again very simple. So let me move on to the next question. GATE 2017 Electronics Engineering Set 1 question number 18. So from that this question is taken. The open loop transfer function is given where p is an integer is connected in unity feedback configuration as shown in figure. Given that the steady state error is 0 for unit step input and 6 for unit ramp input, the value of the parameter p is dash. That means they have given the steady state error information for unit step input and ramp input. They are asking what is this power p, what is the value of p. Since they have given steady state error as 0, it is very certain that it should be a type 1 or more than that. Moreover, they said it is constant for a unit ramp input. Always type 0 system means step input it will be constant, ramp input it will be infinity. If it is a type 1 system, step input it is 0, ramp input it is constant. So that is what they have given. That's all. So step input steady state error is 0. 1 by 1 plus kp we know. So step input kp is what? Limit s into 0 g of s h of s. So p has to be definitely non-zero. Therefore limit s into 0 this will be infinity. You can substitute as s tends to 0. If p is non-zero, definitely all this this will be a 0. This is a constant. So constant divided by 0 is infinity. For ramp input they have given 6. What is ramp input? Steady state error expression 1 by kv. What is kv? Velocity error constant. That's all. So velocity error constant, limit sn into 0, s times g of s h of s. So limit sn into 0. So s plus 1 by this, same thing, multiplied by s. That's all. Now they have given 1 by 6. They have given the steady state error as 1 by 6. Steady state error is 6. I'm sorry. Steady state error is 6 means, that is 1 by kv 6 means, what is kv? It should be 1 by 6. So if it has to be 1 by 6, p should be 1 only. Because if you substitute p as 1, s power 1, s plus 2, s plus 3. So s cancels. So s plus 0 plus 1, 0 plus 2, 0 plus 3, 1 by 6, 1 by 6. That is what I said. Straight away you can conclude this, because ramp input constant, step input 0 means it should be type 1 only. So s power 1, s power 1. So they have given the steady state error. That means for ramp input, kv should be 1 by 6. So s into g of s. So yes, that s power 1 cancels. 1 by 6, that's all. See, we can straight away conclude this just by saying this. Only thing is you have to apply, that's all. Next question. Consider the following closed loop control systems where g of s is 1 by s into s plus 1, and c of s is k into s plus 1 by s plus 3. The steady state error for unit ramp input is 0.1. What is the value of k? So they have given two functions. The c of s is controller transfer function. Normally c of s will be used for output, but here y of s is used for output, c of s is used for the controller transfer function. So the controller transfer function is that k into s plus 1 by s plus 3. So g of s is 1 by s into s plus 1. Anyway, h of s is 1 because it is unity feedback. Therefore, finally, the loop transfer function g of s and h of s means c of s and g of s into this. That means we have to simply multiply whatever is given. K into 1 by s into s plus 1 into s plus 1 by s plus 3. Steady state error for a unit ramp input they have given. Last problem only steady state error for unit ramp input they have given as 6. Here they have given 0.1, that's all. So if it has to be 0.1, then kV should be 1 by that, because steady state error for a unit ramp input is 1 by kV. Therefore, what is kV? 1 by steady state error. That's also that logic we have to use. So first we have to find out kV. So if you find out kV as s tends to 0, s into g of s, h of s. So same expression multiplied by s. So s cancel each other. 0 plus 1, 0 plus 1. So 1 by 3 into k. So k by 3. So what is steady state error? 1 by kV. What is that? Reciprocal of this? 3 by k. 3 by k should be equal to 0.1. Therefore, what is k? K is 3 by 0.1, which is 30. So k is equal to 30. So 3 by 0.1, which is 30. So see how easily we can solve. So GATE 2018 electrical engineering, question number 46. The unit step response y of t of a unit E feedback system with open loop transfer function g of s h of s equal to k by s plus 1 whole square into s plus 2 is shown in the figure. The value of k is dash up to 2 decimal places. So they have given the step response, unit step response, and they are asking what is the value of k, right? See, here we can find out the response is settling down at 0.8. The response is settling down at 0.8. Step input, unit step response means step input. So we are giving 1 as the input, but output is 0.8 only, steady state output. So why we are getting that 0.8 only instead of 1? That is, there is a steady state error. Why? Because it is a type 0 system. See, pole at origin is not there. S term is not there. S plus 1 whole square is there. S term alone is not present. Therefore, steady state error is 0.2. That is what I have written. Symbolically, I have written limit t tends to infinity, input minus output. Because this is a steady state error expression. Limit t tends to infinity, E of t. Right. What is steady state error? For a step input, we know limit s into 0, s into E of s in S domain by final value theorem. So we know for a step input, it is 1 by 1 plus kp 0.2. And if we find out kp from this, what is kp? Limit s into 0, g of s, h of s. So if you find out kp, it is k by 2, because 0 plus 1 whole square, 0 plus 2, so k by 2. And the steady state error is 0.2. We have found out based on this graph on the given input. Input is 1 and the graph it is settling down at 0.8. So 1 minus 8, 0.2. Therefore, this kp we have to substitute here and solve this. Find out k, that's all. See how simply we have solved it. So next question. So it is taken from GATE 2020 Instrumentation Engineering, question number 37. So we can see they have given the time response y of t. So the gain of the system is dash. So here again the problem is like the previous problem. The steady state error we have to find out. So steady state error input is 10 u of t. So 10 times the step, unit step. Output is 8, so steady state error is 2. Since it is 10 times unit step, we have to use the steady state error from the fundamentals. Steady state error from the fundamentals is limit s into 0, s times r of s by 1 plus g of s. So that is 2. So r of s is 10 u of t means 10 by s by 1 plus g of s. So g of s is this. So from this you can find it is 10 by 1 plus k. S cancels. So 1 plus k by 1. So 10 by 1 plus k is 2. Therefore k plus 1 is 5. So gain of the system is 4. That's all. So here it is unit step response. They have said it is from g of s equal to this. Y of s is g of s by s. Forced response is dash. That means they have given the forced response as g of s by s. G of s is given. Now they are asking what is y of t. See, very simple, sir. This expression divide by s. You get y of s. Take partial fraction. That's also you take partial fraction. How will you do partial fraction? A1 by s plus A2 by s plus 1 plus A3 by s plus 3. Do partial fraction. So after doing partial fraction, we can find that we get this. 1 by s on inverse Laplace transformation is 1. Normally 1 means we write u of t. U of t means it is 1 when t greater than or equal to 0. That's all. Because they are not given 1, they are given in terms of u of t. 1 by s plus 1. S plus 1 means 1 by s plus 1 means e power minus t. Laplace transformation of e power minus t is 1 by s plus 1. So 2 e power minus t, again they have given u of t, because this exists only when t greater than 0, greater than or equal to 0. So 1 by s plus 3 again e power minus 3t, like here e power minus t, it is e power minus 3t, there is no 2 here 1, e power minus 3t u of t. So this fits into option A. So option A is correct, that's all. So next problem. It is taken from GATE 2019 Chemical Engineering question paper. Choose the option that correctly matches the step response curves on the left with the appropriate transfer function on the right. The step input change occurs at time t equal to 0. See, there are 4 step responses. One is the step response is increasing and then it is becoming steady. One is it is increasing, again it is increasing infinitely. One initially it is going negative, then increasing, then it is becoming steady. One initially it is like an impulse, then it is decreasing, then it becomes steady. And they have given 4 options. Now we have to see which option is correct. First we will see the first transfer function. So if we see the first transfer function, that first transfer function is written here, rewritten. So s square term is there. So you can do partial fraction as a by s square plus b by s plus c by s plus 1 by tau. Right? Because we can take this tau outside, then s plus y 1 by tau, the tau can be taken to the numerator. Of course, we are not worried about the solution, exact solution. Now, if you see the nature of the response, a by s square means at, b by s means b, this is c into e power minus t by t. So, what is very clear from this is, initially it is rising linearly and you have a constant, and this c into e power minus t by t, as time tends to infinity, this is going to be 0, this is going to be 0. So finally only these two are going to matter. So a into t plus b. So a into t plus b. So that means it is an rise, completely rise, a into t plus b. This is anyway 0 at infinity. So this is going to be falling, exponentially decaying. This is linear rise, this is a constant. So it has to be a rising one. At t equal to 0, it should be 0. This is 0, right? And this is some constant. So it is starting from 0 or some value, but it is increasing linearly. Then it is going like this. Initially some slope, thereafter slope changes because of these two terms. So only here it is rise like this, nowhere it is rise. Therefore This Q and 1 they are matching. Q and 1 matching among the 4 options, if you see only in B, Q and 1 matching. So no need to see other options at all. Since Q1 is only in option B, we don't have to check the other matches. Therefore option B is correct. So it is by elimination principle. That's all. So see how easily we have done. So it is taken from Instrumentation Engineering. A second order system has got closed loop poles located at some place. So what is the time at which the maximum value of the step response occurs? So we have to give the answer corrected to 2 decimal places. So time at which the maximum value of the step response occurs means peak time they are asking. Closed loop poles they have given as complex poles, so definitely it is a second order system problem. What is second order system? Closed loop poles are given by minus zeta omega n plus or minus j omega n square root of 1 minus zeta square. Therefore, if we compare these two, zeta omega n is 3, omega n root of 1 minus zeta square is 4. Therefore, omega n root of 1 minus zeta square is 4. What is peak time expression? Pi by omega n root of 1 minus zeta square for a second order system. This you would have studied in second order system chapter in control systems. So, omega n root of 1 minus zeta square is 4. Pi by 4. Pi is not 180 degree, it is radians. So, 3.1414, that is 22 by 7 divided by 4. 0.79 seconds. So, peak time is 0.79 seconds. That's all. Corrected to 2 decimal places. See how easily it is done. It is a numerically answered type, so no option is given. So next they have asked a question from GATE 2016 Electrical Engineering. A second order real system has the following properties: damping ratio, omega n, steady state value to a unit step input is 1.02. What is the transfer function of the system? They are asking what is the transfer function of the system. See, we know very well that a closed loop transfer function of a second order system is given by omega n square by s square plus 2 zeta omega ns plus omega n square. See, normally for the steady state output to a unit step input is 1. Because if you find out the steady state output, it will be 1, right? Because you can apply the final value theorem, and we would have seen for this it is 1 only. Steady state is 0. Therefore, output follows the input. But as per the specifications given, steady state value is 1.02. That means some 1.02 is multiplied. Therefore, the closed loop transfer function is not in this form. 1.02 into omega n square by this form. So, what is omega n square? Omega n is 10. So, 10 into 10, 100. What is 2 zeta omega n? 2 into zeta into omega n, substitute 10. So, s square plus 2 zeta omega n is 10s, omega n square 10. So, omega n square is 100. 100 into 1.02, 102, because steady state value is 1.02. If it is not there, then we could have taken it as 100. Therefore, this fits into this option. Some of the people may get confused with this. We should not take this because steady state value is 1.02. If it is 1 means this would be simply this. That is the difference. See how simply we have done it. So how easily we have done it. So block diagram of a closed loop control system is given. So the values of K and K and Kp are such that the system has damping ratio 0.8, undamped natural frequency of 4 radian per second. What is the value of Kp that they are asking? So G of s is known to you, H of s is known to you. They have given damping ratio, natural frequency, all that. Therefore, we have to bring it to a standard form. So we will find out C of s by R of s. So this is G of s. So G of s by 1 plus G of s, H of s, this is H of s. So take the LCM, simplify, we will get like this. So here K is omega n square. Last problem only we have seen. This is the standard form, omega n square by s square plus 2 zeta omega n s plus omega n square. So that is what given here. So K is omega n square. Then 2 zeta omega n is 1 plus KKP. That's all. So K is omega n square. And they have given omega n as 4. 4 square 16. 2 zeta omega n. Damping ratio is 0.8, so 0.8 into 4 is 6.4. That means this 2 zeta omega n equal to 1 plus KKP. So 1 plus KKP is 2 zeta omega n. 1 plus K value we have already found out as 16 because K is omega n square. K equal to omega n square. K omega n square, K omega n square. 1 plus 16 Kp equal to 6.4. What is Kp? Solve this, that's all. See how simply we have done. So here the problem is they have given G of us, R of us is unit step input, C of us is the corresponding output, time taken by the system output to reach 94% of the steady state value. So it is again very simple. We have to find out first of all C of t. They have given 94% of steady state value. Therefore, we cannot simply do it using final value theorem. We have to solve for C of t. So the G of us is given and we know R of us is 1 by S. So transfer function output by input is transfer function. Therefore, output is transfer function multiplied by input. So 1 by 1 plus 2s plus s square into 1 by s. So 1 by s into 1 plus 2s plus s square is, if you simplify this, s plus 1 whole square because s square plus 2s plus 1. That is what written here. So 1 by s into s plus 1 whole square. Do the partial fraction. If you do partial fraction, you get like this. So if we take inverse Laplace transformation, 1 minus e power minus t minus t into e power minus t. So 1 by s plus 1 whole square, you have to apply the first shifting principle. So t into e power minus t. Because Laplace transformation of t is 1 by s square. Now s is replaced by s plus 1. Therefore, you have to multiply it by e power minus at. Here it is minus 1. That's all. So you can refer the Laplace transformation pair table. Then you can easily do it. Right. Now steady state value of output, we know it is 1. Why? Because as t tends to infinity, this is 0. This is infinity, but this is 0. Infinity 0 multiplied by 0. So 1. So it works out correctly. Now the question is time taken to reach 94% of steady state value. Therefore, we have to equate the C of t expression to 0.94 because steady state value is 1. Therefore, 94% of steady state value is 0.94. So equate this to this. So you solve this maybe by taking natural logarithm or something, logarithm on both sides, or you can use your calculator and find out. If you find out t is equal to 4.5, if you substitute, you will get the right hand side, right? So t is equal to 4.5, if you substitute, you get the right hand side. Anyway, you solve this and check it out. So t is equal to 4.5 fits into this. Since the options are given, you can substitute one of these options and check. Otherwise, you have to solve. Options are given. It is not a numerically answer type. So our job is simple. So 5.25 it will not satisfy. 4.5 it is satisfying. So option B is correct. That's all. So this is another problem, chemical engineering question paper. So what is the natural period of oscillations they have asked? Anyway, for the want of time, I cannot go through all the questions with explanation for all the points. I'd like to show you this presentation. That's all. So what I have done is I have written the expression for C of t. From that, anyway, C of t, here it is y of t. They have given y of t, so y of t I have written. So we need to find out peak overshoot. So overshoot they have given and they are asking natural period of oscillations. So I am finding out the overshoot. So how I am finding the overshoot is, so we know how to find out the peak overshoot. So peak overshoot is this value. This is the peak overshoot value. So this value I am finding out. That's all. So if you find out it is 80%, so I am equating the second order transfer function expression peak overshoot, finding out zeta. And peak time they have not directly given, but if you take this, this is the peak time. This is 200 minutes. Therefore, this is 50, 50, 50, 50. So peak time is 50 minutes, right? So at 50 minutes it reaches the peak overshoot. So peak time expression is equated to 50. and finally the natural period of oscillations we can find out. So we can do this, right? So I'll wait. You can go through this. So it's very easy. So they have asked you to find out the amplitude ratio. Amplitude ratio means the gain. So we have to find out the gain, and they are asking at 0.5 radian per minute. Now what is that? So we have to simply substitute. This also you can see later due to the want of time. I'm just skipping this. So this is a problem in Rouse stability criteria. So they are asking which of the options is correct for the system shown below. So route stability criterion you have to do from the characteristic equation. So G of S, H of S is done. Characteristic equation. From that route array formed, then seeing the first column of route array, we can see whether it is unstable or not. And unstable, and it is fourth order. So fourth order unstable, option C is correct. So you please go through this. So the last is they have given another question wherein the integral compensation they have given some value, and k by s and g of s is given. What is the positive value of k for which there are exactly two poles of the unity feedback system on j omega axis? So that means this is a problem related to again Rouse stability criterion, because they are asking poles on the j omega axis. So whenever we want to find out the poles on the j omega axis, we have to get row of zeros condition. Row of zeros condition we will get in odd power s row. Then you have to formulate the auxiliary equation, and roots of auxiliary equation you will get the this particular condition. That is what done. So characteristic equation is formed from the characteristic equation route array. So for a system to have poles on j omega axis, or as I said, so finally k equal to 6. Anyway, for the want of time, I have simply covered the last few problems at a higher speed. So I can go through this. Similarly, this problem also it is again based on the Rouse stability criteria. So you can I skip this, so you can go through this. The same method, but it is a conditional stability problem. So what is the range of k for which the system is stable? That is what asked. So the characteristic equation is given. From the characteristic equation, route array is formed. So from the route array, what about the first column elements? So if all the first column elements are positive, what is the condition? All that we have to see. That's all. Same method. So I think I have covered most of the problems. Because of the time limitation, I have rushed up the last few problems. So for your information, this is my channel, YouTube channel. So these are the different videos covering the different topics in the control systems, regular control systems lecture series. So these are again the different topics. So I have covered the entire control system. So introduction to control systems 2, modeling, block diagram algebra, time response, steady state error, stability, all that. So what are the prerequisites for learning all this? What are the URLs of the different videos I have given? Similarly, for other topics like time and frequency domain specification, correlation, Nyquist stability criterion, Bode plot, all that, compensators, speed PID controllers, all that. So what are the prerequisites for the learning? All that I have given. The URLs of the videos are also given. So I have given some overview also in Dr. C. Ganesh teaching modules, that also you can refer. And I have done some gate modules. I have done some gate modules also as content in the YouTube channel. So these are the different videos. So you can go through this. And I have given clearly my objective of this. So Dr. C. Ganesh teaching modules, this is the channel URL. So I want you to utilize this videos by viewing this channel, videos in the channel. So kindly share these videos with your friends, and see that everyone is benefited. So I wish all of you the very best to face GATE 2021 successfully and score as much as possible. And if you have any doubts, you can ask me. You can also post your queries or comments or feedback to this mail ID. You can WhatsApp your comments or queries here. So I thank you very much for your patient listening. So I once again thank the organizers, Dr. Mahalakshmi, Dean CAA, KITCBE, management principal, faculty members and students for giving me the wonderful opportunity to share my knowledge on control systems with the young budding engineers. Thank you.